Okay, good day. So we will be discussing about combustion. So in marine engineering, combustion. So for combustion, we need three elements. We have the fuel, oxygen, and heat. Okay, so for fuel, there are different types of fuel on board ship. We have the diesel or gas oil, light fuel oil, heavy fuel oil, liquefied petroleum gas, LPG, liquefied natural gas, LNG, methanol, ethanol, and so much more. Okay, so there is carbon content. So diesel gas oil has higher carbon content than the light fuel and heavy fuel oil. The LPG also, then liquefied oil, then methanol and ethanol has lower carbon content. Okay, so another component, we need the next element would be oxygen. So oxygen will be used to create combustion. So oxygen also used for our lungs, or so that we can breathe. Okay, next is heat. So you need heat to create ignition. So this ignition will create the combustion process. So content with oxygen, air, theoretical and practical, fuel molecules, law of Lavoisier, emissions, exhaust gas. So I don't know how to pronounce this one. Okay, part 1, complete combustion. So when all fuel is burned with a precisely amount of oxygen, so the air and fuel ratio is exact. So the air we need for this is called the theoretical air volume. So to have a complete combustion. So for diesel engine, but we need more for diesel engine. Why? So we need more air for our diesel engine to increase its power, because the more air you put, the higher the power it will create during combustion, and then the lesser fuel that you will be using. So you will be saving fuel. So more air volume, lesser fuel, but with the same power output or more. RPM and time related, cleaning and cooling with extra air. So the purpose of more air is for cleaning and cooling also. So extra air will be used to clean and to cool down the components inside the engine. Also for RPM to time related, so the faster the more air we put, the more is this for the more RPM. Okay, for this is the 2-stroke and the 4-stroke diesel engine. For 2-stroke, RPM is slow running engine and needs a lot of air for cleaning and cooling. So this is used for 2-stroke engine. While for 4-stroke engine, its RPM is in medium to fast running engine. It uses less air than 2-stroke needs. So it uses less air because it has a better cooling, because it rotates twice to complete the 4 events. So the air factor for combustion is 2 for 2-stroke. Cleaning cooling is 1.2, so a total of 3.2 lambda or air factor. 3.2 for 2-stroke. But for 4-stroke, which uses less air, so you will need an air factor of 2 for combustion, an air factor of 0.8 for cleaning and cooling, so a total of 2.8 air factor for our 4-stroke diesel engines. While for our kettle or boiler, they only have an air factor of 2. For gas turbines, it has an air factor of 1.02 to 1.05. Lesser air factor. Next, let's go with the fuel molecules. So fuel is a mixture of different molecules. A molecule is the smallest part with all the characteristics in it. A molecule is built up with atoms which are connected to each other. So burning is a chemical process where these connections will break and make other connections. So what is here is a hydrocarbon compound. So the more carbon and hydrogen, so methane has just one atom of carbon, so it has less carbon dioxide during combustion. Ethane, C2H6. Propane is C3H8. Butane, pentane, hexane, heptane, and octane. So by the name itself, pentane is 5, hexane 6, heptane 7, octa is 8. So 8 carbons. Let's go. Okay, so how does hydrocarbons or how does fuel is created? So crude oil is heated to more than 300 degrees Celsius, and then at different temperature the lighter fuel goes up and the heavier fuel goes down, and then thereby creating different kinds of fuel. So the lighter fuel has less carbon, while the heavier fuel has more carbon. Okay, so let's go. We have the oxygen gas, we have the H2O, and we have the CO2 gas. So two atoms of oxygen and 1 carbon. Here we have 2 hydrogen and 1 oxygen, and for O2 2 oxygen. So in chemical process, fuel plus oxygen, so this is fuel, like for example let's use methane, 1 carbon with 4 hydrogen, plus oxygen is equals to water plus carbon dioxide. So that is chemical process. Okay, so if you want to have a balanced chemical process, so CH4 plus O2 is equals to H2O plus CO2, add an extra heat. So before and after the process of burning, the amount of atom must be the same. So to balance this one, we have one C here and 1 C here. We have H4 here and just 2 H here. So you just have to put 2 in here to create 4H. 2 times 2 is 4. And then for oxygen, we have 4 oxygen, so you should put 2 in here. So that is the law of Lavoisier, law of conservation of mass. Mass is neither created nor destroyed during chemical or physical reaction. So the total mass of reactants is equal to the total mass of products. So that is Antoine Lavoisier. Okay, so burning of methane. So how do we balance this? So with this one, we have 1 carbon of 1 carbon, so the same with in this part. We have 4H, so we have 2H here times 2 here, so we have 4H, so that these are equal. For O2, we have 2 times 2, so 4 atoms of oxygen. So let's check here. We have 2 oxygen and 1 oxygen times 2 here, so 4 also. So that is a balanced equation. So for diesel oil with C14H29, so many. So this is a polyvinyl acetate or diesel oil. So if you want to combine this one, you should have an equal distribution. So to do this, so this one will be the answer. So just check it, just screenshot it and do it on paper, or how did they do this. Okay, so we have the different weight of the atoms on our periodic table of elements. So atomic mass for hydrogen is 1. 1 mole is equal to atomic mass in grams. 1 kilomole is equal to atomic mass in kilograms. So hydrogen has 1 mole, carbon has 12, oxygen has 16, and sulfur has 32. So if these are the atomic mass, so CH4 is equals to 12 plus 4, which is equals to 16. C is 12 and H is 1 times 4 is 4, equals to 16. So the atomic mass for CH4 is, or what is this, methane, is 16. While for oxygen gas, the atomic mass is 2 times 16, which is equals to this is oxygen gas by to the power 2O2, so 64. CO2, 12 plus 16 plus 16 is 44 atomic mass. For H2O, 2H2O is equals 2 times 1 plus 1 hydrogen, 1 plus 1 plus 16 oxygen equals 36. So that is the atomic mass. So when you want to burn 16 kilogram of methane, you need 64 kilogram of oxygen gas. Based on this one, if you want to burn 16 kilogram of methane, you also need 64 kilogram of oxygen gas, and your product will be 44 kilogram of CO2 and 36 kilogram of water evaporated. Wow. Okay. So in this equation, we have 1 kilogram of CH4 plus 2 times 2, so 4 kilograms of oxygen gas is equals to 1 with CO2 44.6 kilograms, so 2.75 kilogram of CO2 plus 2.25 kilogram of H2O. If you want to, this is the amount you need. Okay, in theoretical airflow rate, so 1 kilogram fuel plus 4 kilogram oxygen gas equals 2.75 kilogram of CO2 plus 2.25 kilogram of H2O. But do we have much air in this? So 4 kilograms O2. So air in the atmosphere contains 23% oxygen. Alright, 22.8. So 23% oxygen. So theoretically, you need for burning 1 kilogram methane of 100 or 20 over 23% times 4 kilograms of O2 is equal to 17,392 kilogram of air. Since 23% of air is oxygen, times 4 kilograms, you will have to 17,390 kilograms of air for 1 kilogram of methane. So much air for 1 kilogram of methane. So that's the theory. So in practice, it is not possible to know exactly which molecules are in the fuel. So that is why it is calculated for each element how much air is needed and how many emissions are generated. So example, a fuel is the following composition. Carbon is 87%, hydrogen is 12%, and sulfur is 1%. So with these elements, we will calculate how much air we need. So C plus O2 equals CO2. 12 plus 32 equals 44. Since 12, carbon is 12, oxygen is 32, 44 over 12. So carbon plus 8/3 carbon is equals to 11 over 3 carbon. Oops. Okay, for atomic mass, for 2H2 plus O2 equals 2H2O. So 4 plus 32 equals 36. 1 plus 8 equals 9. So hydrogen plus 8 hydrogen equals 9 hydrogen. So S plus O2, sulfur oxide. So this is SO2, sulfur oxide. We have 32 sulfur and 32 oxygen equals 64 of mass. So 1 plus 1 equals 2 if you want to factor it out. So S plus S is equals to 2S. So for these given elements, we need oxygen. 8 over 3C plus 8H plus S. So air consists of 23 oxygen. Theoretical airflow is 100 divided by 23 times 8 over 3C plus 8H plus S. So the final answer is 14.3 kilogram of air per kilogram of fuel. So this fuel had the following composition: 87% H and S, CHS. What fuel is this? So for emission, CO2 is equals to 11/3 C, which is 3.9 kilogram per kilogram of fuel oil. For SO2, sulfur oxide, S plus O2 equals SO2. So 0.02 kilogram per kilogram of FO. So emission exhaust gas. So now that we know the theoretical amount of air required for this kilogram fuel, we are now going to look at the engine, its consumption of fuel and air needed for the process of combustion. So the data, we have a 4-cylinder 4-stroke engine with RPM of 540 per minute, 2 gram per injection of fuel, air, theoretical air of 14.3 kilogram per kilogram fuel, with a air factor cleaning of 1.25 and air factor combustion of 2. So asked, A, the mass of flow fuel, the mass, letter B, mass of flow air, and C, the mass flow of exhaust gases. Okay, so the rotation of 540 per minute must be converted to per second. So 540 divided by 60 is equals to 9 per second, so 9 hertz. Number of process per second. So we have 9 per second times the number of cylinders. So what is the number of cylinders? 4-cylinder engine. Process constant of 2, which is equals to 18 per second. So the mass flow per injection equals 2 grams. So 2 times 18 equals 36 grams of fuel per second. which is 3.036 kilogram per second, or 3.11 tons per day. So the mass flow air, so mass flow air times air, thermal theoretical air times the air factor for combustion and cleaning cooling. So the total is 1,287 kilogram of air per second. So the density of air is 1.29 kilogram per square meter, or this cubic meter. So square meter, and then so it is equals to 1 square meter per second of air. Let's go with the mass flow of exhaust gases. So the law of Lavoisier, mass in is mass out. So fuel with 0.036 kilogram per second and air with 1.287 kilogram per second. So mass of fuel plus mass of air equals to mass of the gas, which is equal to 0.036 plus 1.287, which is equals to 1.323 kilogram per second of exhaust gases. So that is the mass flow of exhaust gases. So many. So emissions of CO2 and carbon dioxide and sulfur oxide. So this fuel are the following composition: C87, H12, and S1. So emission of CO2, CO2 is equal to 11 over 3 carbons times 0.87 is 3.19 kilogram of FO. The mass of fuel is 0.036 kilogram per second. So our CO2 emission will be 0.115 kilogram per second. So emission of SO2, 2 times S is equals to 2 times 0.01 equals 0.02 kilogram SO2 per kilogram of fuel. So the mass of fuel is 0.036 kilogram per second. So multiply both. The answer will be 0.00072 kilogram of sulfur oxide per second. So there are so many computation. Okay, so here we have the injector, fuel injector, and then a temperature of 350 kilogram. There is cold fuel injected by the injector. And then at this part there is 825 Kelvin warm air. And then at this part there will be rich air fuel mixture, so mixture of air and fuel at 825 Kelvin. At around 1600 Kelvin there is products of rich combustion, carbon monoxide, hydrocarbon, and particles. And at the tip part of the fuel fire, we have 2,700 kilogram with NOx and CO2 and H2O production. So diesel fuel plus air is equal will produce major exhaust constituents CO2, H2O, N2, and O2. We have exhaust components found in trace concentration: NOx, hydrocarbon, carbon monoxide, SOx, carbon plus PM, or particulates matter. So let's go with NOx, or nitric oxide, nitrogen oxide. In the previous picture you can also see the NOx, which is also an important greenhouse gas emission. So nitric oxide has 3 formation mechanisms. So nitrogen as an element in the fuel NOx. Nitrogen from excess air reacts with oxygen gas during combustion with thermal NOx. The higher the flash point, the more NOx is formed. Reaction of nitrogen compounds with free oxygen radiance prompt NOx. So products of incomplete combustion, we have the carbon monoxide, hydrocarbon, we have carbon, we have particle matter or particulates matter. So for combustion, so that's it for combustion. Okay, so the last part will be the products of incomplete combustion. So it is better to have a complete combustion to prevent or lower down these byproducts, which is very detrimental in our greenhouse gas emission and which is detrimental in our environment. So that's it for combustion. So very long computation with chemical composition. Okay, so I hope you learned something today, and I'll see you on the next one. Goodbye.